Hello, everyone. This is Marwan Omar, and I'm from Illinois Institute of Technology. I'm an associate professor of cybersecurity. Today, my presentation is on text defend, detection adversarial examples using local outlier factor in the NLP domain. I appreciate the organizer of this conference, and I'm excited to be the keynote speaker today. Here is the outline. We are going to start with an introduction and motivation to the problem statement. We are going to talk about our data set collection. Then we will move on, talk about the methodology that we use for implementing our technique, then evaluation and discussion of the results, and then we'll wrap up with a discussion and conclusion with future work. Introduction and motivation. Introduction to deep neural networks. Deep neural networks are known to be vulnerable to what we call them adversarial attacks or adversarial examples. Adversarial attacks are techniques that are used to perturb the input data to force an NLP model or language model to produce incorrect predictions or fool the NLP classifier to making the incorrect predictions. This presents a fundamental weakness in the training algorithms for NLP models or systems. In this slide, we are going to talk about a specific example related to the security and vulnerability of deep neural networks. As we mentioned, DNNs are vulnerable to adversarial attack. So here is an example. Imagine we have a text example. It says, connoisseurs of Chinese film will be pleased to discover that Tian's meticulous talent has not withered during enforced 80s. This is an original input text for a text classification system. This is a sentiment analysis task. If we were to feed this sentiment to an NLP classifier, meaning a language model that is going to predict, it will predict that this is a positive sentiment from a customer, from a review. This is a positive review from a customer with 77% confidence. However, by making some minor changes, if we just simply create an adversarial example by changing a couple of letters in this example, in this case, we will replace letter C with letter A. So it will be connoisseurs of Chinese film will be pleased to discover that Tian's meticulous talent has not withered during his enforced 80s. By making this change, we are launching an adversarial attack or adversarial example on an NLP classifier. This will fool the NLP classifier. So now the NLP classifier will predict this with 52% confidence that this is a negative sentiment. This is an example of an adversarial attack. Another variation of adversarial example would be the following. Rather than using the word film, we will use the word footage. They are similar to each other. So this is semantically similar. The meaning does not change. The semantic of the review shouldn't change. However, the NLP classifier is tripped and is fooled to make the incorrect prediction, even though this was originally a positive sentiment. Now the NLP classifier is classifying it as a negative sentiment with 54% confidence. So this is what we are trying to do in our paper. In this paper, we are trying to detect these adversarial examples. The contributions of the paper are as follows. We will propose the usage of local outlier factor to detect and eliminate adversarial examples targeting text classifiers. We demonstrate that local outlier factor, or LOF for short, can be used to counter 3 different adversarial attack recipes, namely text bugger, genetic, and deport bug. Our results show that pre-processing the dataset with LOF restores the performance of most popular text classification architecture, such as BERT, WordCNN, and LSTM, on 3 different social media datasets. Here is more information about our technique. So this is the local outlier factor, which is a density-based outlier detection method that investigates the density of an object and that of its neighbors. The object here is identified as an outlier if its density is relatively much lower than that of its neighbors. And here's the math notation behind our local outlier factor. We are going to calculate the local reachability density of an object O and compare it with that of its neighbors and quantify the degree to which the object is considered an outlier. Here is a demonstration of the basic notion of the local outlier factor. We can see here on my left, there's a dot, and we have letter A. This black dot or circle is further away from the rest of the black dots. So this would be an outlier, and this is what the local outlier factor does. It calculates the distance, so the distance between the other black circles is much smaller than the distance from A to the other circle. So in this case, A would be considered an outlier, which would be an adversarial example, and our goal is to detect and eliminate that. Here is our proposed solution. So we have a real-world data set or data sets. We are going to pre-process it with a local outlier factor to detect adversarial examples. If we find adversarial examples, we are going to drop them, eliminate them. If not, then we will feed these data points, which are part of the real-world data set, to the NLP classifier, so the NLP classifier can reliably classify the data point. Now we are going to talk about data collection. So here are the details of our data sets. Table 1 shows that we utilize 3 benchmark data sets, namely Yelp, MR, and AG News for our sentiment analysis task and also sentence classification. So we decided to tackle 2 tasks. One is the sentiment analysis and the other is the sentence classification. The Yelp as well as MR datasets have binarized ratings and is set as positive and as negative, and split into training, validation, and test sets. So the Yelp dataset includes a set of 560,000 data points for training, another 38,000 for testing. MR dataset, which is the movie review dataset, it has a set of 5,331 data points for training and the exact same number for testing. And then for the AG News, which is a news topic classification, we have a set of 120,000 data points for training and 7,600 data points for testing. Now we are going to talk about the model architectures. As we mentioned briefly, we used 3 different model architectures. We used BERT, which is a transformer. We used WordCNN, which is a convolutional neural network, and LSTM, long short-term memory. We are going to talk about the results and the evaluation. These are the evaluation metrics that we use. These are classical metrics for machine learning. So we have the precision, the recall, and F1 score. We show now the baseline and accuracy under adversarial attacks. So we evaluate the performance of 3 NLP classifiers, as you mentioned: BER, WordCNN, and LSTM. Prior to the implementation of our LOF technique, we utilized text attack framework and implemented the attacks using deport bug attacks. Table 2 will show us that the model classification accuracy in the adversarial examples is significantly low. It's shown that LSTM model fares the worst when exposed to adversarial attacks. So here we show again different data sets, the different models, and the accuracy. So for example, as you can see here, in the AG news, we have three models again, BERT, CNN, and LSTM. When we attack each one of these models with adversarial attacks before implementing LOF, we can see the accuracy is low and the attack success rate is high. So the accuracy is just 21.9% for BERT on AG News. It's 12.97 for the MR and only 9% on the Yelp dataset. This is significantly low, and this is because we have no protection. Then, after we implement the local outlier factor for detecting adversarial examples on the same three classifiers and using the same three data sets, the goal is to see how effective our technique is in detecting and eliminating adversarial examples. So we noticed that BERT classifier fared best with a classification accuracy of up to 92.59 when tested on the Yelp dataset. On the other side of the spectrum, we noticed that LSTM fared the worst with a classification accuracy of 65.78 when evaluated on the AG News dataset. Here is more information about the results. So we have the same data sets, AG News, MR, and Yelp. The models again, BERT, CNN, and LSTM. After implementing our local outlier factor technique, we can see that the accuracy has gone up significantly, literally from 20%, 21% to now 89% on the AG News. Where CNN now has a classification accuracy of 82%. On the Yelp dataset, BERT did really well, achieved 92%. So this goes to show the effectiveness of the LOF technique in detecting adversarial examples. And of course, the attack success rate goes down here because of our LOF technique. ASR stands for attack success rate. The attack success rate is only 14.78 on AG News. It's only 15.98 on MR and only 13.94 on the Yelp dataset. So again, this goes to show the effectiveness of the technique in detecting adversarial examples. So to sum up, you observe that BERT is consistently performing the best among the other two network architectures, CNN and LSTM, when the other variables, dataset, and attack recipe are controlled. This is not surprising as BERT is a transformer-based learning model and is known to achieve state-of-the-art performance under various linguistics tests, including sentiment analysis and sentence classification or topic classification. Here are detailed results as we compare it to this and FGWS. This and FGWS are two techniques from the literature, and we use them as baselines. And we can see that LOF outperforms both alternative methods across different data sets. To conclude, vulnerabilities in NLP models can yield a serious safety risk. In this work, we describe and empirically validate a new technique based on the local outlier factor algorithm to detect adversarial examples in the NLP domain. We employed real-world data sets and numerous network architectures, including transformer-based model, CNN, and LSTM. Our empirical findings indicate that our LOF technique is capable of detecting adversarial examples with an accuracy of up to 92% on the Yelp dataset for the sentiment analysis task. To validate the competitiveness of our approach against existing work, we tested our technique against 3 attack recipes using the same data sets and models above. Again, BERT, CNN, and LSTM. Our empirical results illustrate that our technique outperforms state-of-the-art solutions with F1 detection accuracy scores of up to 94.8. We are intrigued to see how our LOF technique performs against out-of-domain datasets. In particular, we are interested in evaluating the performance of our approach in the malware and anomaly detection domain of cybersecurity, which is a future research direction worth pursuing. So that was the presentation. Again, the title of the presentation was to use text defend, which is a technique for detecting adversarial examples on local outlier factor. Once again, thank you for your time and attention, and thank you for the conference organizers and the committee members for giving me the opportunity to present at CONF-CIAP. Thank you.